All right, howdy y'all. Welcome to my presentations. We're going to start with 6.10. So if we have three numbers, p, q, and r, greater than 0, less than or equal to infinity, with a strict inequality, p less than q less than r, then we have that LP intersect LR is a subset of LQ, and we get this nice inequality here, where the function f in their intersection in the q norm is less than the r norm times the p norm with exponents 1 minus lambda and lambda. Here where lambda lives between 0 and 1 and is defined by this quotient here. And the intuition for this quotient definition is that if we were to consider this function of t, so we'll call it phi of t, equal to t inverse plus 1 minus t r inverse. This, as t ranges from 0 to 1, when t is 0, we have r inverse. When t is 1, we have p inverse. This is a smooth transition from one to the other. We're picking the value for lambda such that this function equals q inverse. So that's the intuition for the definition of lambda. So here, lambda is equal to, lambda is defined such that this is equal to q inverse. Okay, that's just the intuition behind it, behind where this definition came from. But it's defined strictly using the quotient. So we're going to break this up into two cases. We allow r to be less than or equal to infinity. So we're first going to deal with the case where r is equal to infinity. Now, this one's pretty straightforward. We know that if we take the absolute value of f raised to the q, that it's less than or equal to the uniform norm of f to the q minus p times the absolute value of f to the p. And the reason that we know this, the reason that this inequality holds, is because if we were to divide f over to this other side, we would have the absolute value of f, q minus p, is less than the uniform norm of q minus p. Well, that's obviously true because this is defined to be the supremum of the function, at least almost everywhere, where the almost all of the function is below. So from this, we get, and then we note that if r is infinity, the reciprocal of r is 0. So then we have that lambda is nicely defined as p over q. From here, what we get, so what we get here is we're going to take the integral of both sides of this inequality. So here we've got the integral of f to the q, and on this side, this thing is just a constant, so it pops out of the integral, and we have the integral of f to the p, the absolute value of f to the p. Now, by taking the qth root of both sides, we get this here, we get a fractional exponent there, and then we get this raised to the 1 over q. Now, we note that the integral of the absolute value of f to the p is the pth root of the p norm of f. So we can write this as the p norm of f to the pth power. So we end up with a p in the numerator here when we write this in the form of a norm. We note that this is just the q norm, and then here we can just break up this fraction so that it's 1 minus p over q. So now, because lambda is equal to p over q, this is in fact, this thing here is just the uniform norm 1 minus lambda, and this is just the p norm to the lambda, which is exactly what we wrote in our original inequality. So in the first case, it's a pretty straightforward integration and root extraction on this equation here. Next, for case 2, we're going to need to notice something. Again, it's not terribly difficult, but you have to notice a very odd fact. So in the case where r is less than infinity, we're going to do a quick computation. So we're going to take lambda q over p and add it to 1 minus lambda q over r. Why? You'll see in a second. It's not at all obvious. So if we do this, we can multiply both, we can find a common denominator here. Then once we found a common denominator, we want to factor out the terms that have the lambdas in them so that we can replace lambda with its definition. So we're going to pull out the only term that doesn't have lambda, put it out at the front, and then we're going to take r lambda q minus p lambda q over rp, and we're going to factor out lambda. So when we factor out lambda, we're going to get rq minus pq, and then in the denominator rp. Then from here, we have this multiplied by lambda. This is our definition of lambda, so lambda's right there. Now we can take this product, we get this guy here, and you'll notice rp times p inverse is just going to be r, and rp times r inverse is going to give us p, and then we just FOIL the numerator. Now we want to find a common denominator again. We get this crazy fraction. Not going to go through every single step. It's basic pre-calc. But we then get to cancel the positive one here with the negative one here, and the negative p squared q with the positive p squared q. And that leaves us with r squared p minus p squared r. From here, we can factor out an rp from the top and cancel with the rp in the bottom, and we get that r minus p over r minus p is equal to 1. So this thing here is 1, which tells us that p over lambda q and r over 1 minus lambda q are conjugate exponents. Which will allow us to use Holder's identity. So now that we have that those are conjugate exponents, we take the integral. Slide this a little forward so you see a little better. Okay, so we're going to take the integral of the absolute value of f to the q, and we're going to say that, hey, that's equal to f to the lambda minus, whoops, there should be a q here and a q here. Okay, so we split this up, 1 minus lambda, lambda plus 1 minus lambda is 1, so that's a valid split up of the product. Then from here, we use Holder's identity, because what we notice is that p over 1 minus, or p over lambda q and r over 1 minus lambda q are conjugate exponents, and this is just the, or sorry, yeah, so this is just the L1 norm of f lambda q f 1 minus lambda q. This is just the L1 norm. So little 1 there. Take it. Ran out of space. So because this is just the L1 norm, we can then split it up using Holder's identity, using the conjugate exponents with our f to the q lambda 1 minus q lambda. Then from here, we write it in its notation, in the standard notation. So this is just the p over lambda qth power of f inside the integral to the p lambda q power. So when we take the, so we can rewrite this as f, the integral of f to the p over lambda q, but it's already to the lambda qth power, so the lambda q's cancel and we're left with p, and then the exponent of it is going to be the, give me 1 second, the exponent to the whole thing, because is going to be the inverse of this, because that's the, because when you take the LP norm, you take the reciprocal, the power of the entire integrals, you take the reciprocal. So same thing here, and we get the reciprocal here. Then when we can compress this back into being the P and R norms. So now when we compress this back into being a P norm, we get rid of the denominator in the exponent, because we have the p norm already has the 1 over pth power, and same thing, we can get rid of the r here because we're taking it as an r norm, so the denominator goes away and we're simply left with the inequality, which is what we wanted originally, that f to the 1 minus lambda r times f to the lambda and the p norm, which is what we get right here as desired, and we're done. Okay. So, sorry if I was a little shaky on that last part. I got a little confused with my with the reciprocal, but yeah, it's there because the LP norm already had, you take the reciprocal of the exponent when you're writing up the LP norm. So in the next video, we're going to jump into section 6.5 and get started with the first theorem in that one. Anyway, I will see you guys in the next video.